Okay, we have a steady two-dimensional incompressible flow due to a spiraling line vortex sink flow centered at the z-axis. Okay, if you look closely, this is a 2D cylindrical problems. Okay, with polar coordinates. This is not like the axisymmetric case, just from before. So our plane is the r theta plane, the polar plane. Okay, and the dimension that's inside, okay, the page is the z dimension. So what we want to find is we are giving two velocity fields, okay, ur and u theta, and uz is 0 because the flow is two-dimensional, and c and k are just arbitrary constants, and we want to calculate the pressure as a function of r and theta. So the pressure as a function of r and theta. This is our goal. We're going to use Navier-Stokes equation for that, okay? Because we need to find the pressure field. And we have the velocity components and the boundary conditions in this problem. So let's start. Okay. The Navier-Stokes equation expansion in the cylindrical coordinates are in these forms. Okay. So if you want to do them, okay, do the math. So the continuity equation is like this, okay, for the incompressible flow, gradient dot v, or the divergence of the velocity, is equal to 0. But what happens here is that the derivative of the unit vector in the cylindrical coordinates sometimes have a value. It's not 1. So sometimes you will have additional terms in the equation. Like look here, this should be 4 terms, the local and the convective, but here 1 term will be added. And here also you should have 3 terms, but here you have 2 terms added. Same thing here, okay? And same thing here also, this term. So if you want to do it, you can do it, okay? We know that this is the material derivative, okay? The material derivative of the velocity, okay? Okay, so you can do this one in the cylindrical coordinates. I will get the same thing. And this one is the second derivative, okay, with respect to the dimension, okay. So the second derivative with respect to dimension, second derivative, the Laplacian term. So you can do the Laplacian also in the cylindrical coordinates, and you will get the same thing. And here is also do the Laplacian operator in the in the cylindrical coordinates for the z component, and you will get the same thing. But anyhow, I got for you the equations ready here. Okay, and the exam is an open book exam, so you will have the equation in hand. So what we have, the flow is 2D. We have UR equal to C over R, and we have U theta equal to K over R. Don't forget those two. And we need to find P as a function of theta and R. So the continuity equation is of no use for us, but if you just want to verify the continuity equation for this flow, derive UR with respect to R, okay, multiplied by R. So UR multiplied by R is going to be C, yeah? So C, the derivative of C here, okay, the derivative of C, okay, with respect to R is going to be 0. And here, U theta, which depends only on R, is derived with respect to theta, so it is also going to be 0. And here Z, which is 0, so its derivative, it's 0. So the continuity equation is verified, okay? But let's start with the actual problem. So we will use two momentum equations, the momentum equation in the R and the momentum equation in the theta. The momentum equation in the Z, okay, because we don't have a velocity component in the Z, everything is going to be 0. So here 0, we don't have a velocity component in the Z, no velocity components. So all the derivatives with respect to Z are 0, and you're left up with those two things, okay? So this will be the variation of pressure, okay, with the z direction. We assume in cylindrical coordinates, okay, that the body forces, which is rho gz, is in the z direction. So here we don't have body forces, here we don't have body forces, which are the gravity. So let's say that it is a cylinder, okay? So the weight of cylinder is in this direction, okay? The weight of the cylinder. Or let me draw it vertically, cylinder for you, okay? This is the cylinder, okay? So its weight is in this direction, which is the z direction, okay? Not in the r direction and not in the theta direction. So no body forces in the theta and no body forces in the r direction. And of course, the only body forces that we use in such problems is, that we have in such problems is the gravity. You can have electromagnetic forces, other type of forces, but for our problems, we only have gravity, okay, usually. So now the body forces here is 0, the body forces here is 0, and here we have the body forces, okay, rho gz. So this will give us the variation of pressure in the z direction, which is not the one that we want, okay, because this will be the hydrostatic pressure, okay, hydrostatic pressure, the one with the z direction. We want the pressure variation in the plane, in the polar plane, with r and with theta, okay, the pressure with r and with theta. Because if you solve this one, you will have minus partial p by partial z equal to minus rho gz, okay? So you cancel the minuses and you will end up with p equal to rho gz, okay, z, okay, plus a constant, okay? And so yeah, so delta p will be equal to delta p rho gz, yeah? And the constant, of course, is going to be the pressure function in the plane of r and theta. We want to find this one, not this. So just ignore it for now. So that's why the z component of the momentum equation is of no use for us. Okay. Now let's continue. First off, we know that the flow is steady. Yeah, the flow is steady. Remember that. Okay, let's bring here the question. The flow is steady and it is two-dimensional. So we use the information that it is two-dimensional. Incompressible, okay, yeah, we use the incompressible Navier-Stokes equation. But here, steady flow, so this means that those two derivatives here are zeros. So no variation of velocity with respect to time, and no variation of this velocity component with respect to time. So delete them. And what also can we delete? We can delete all the derivatives with respect to the z, yeah, because we don't have the velocities are only functions of r, yeah, k over r and c over r. So as well, we can also omit the derivatives with respect to theta. So every derivative with respect to theta or with respect to z, omit it. This one, okay, because the velocity of ur does not change with theta, ur does not change with z, ur does not change with z, ur does not change, u theta does not change with theta, ur does not change with theta. Same thing here, u theta does not change with z, and ur does not change with theta, and u theta does not change with theta. Same thing here, and yeah, same thing here. So in the end, this is what is left for us. Okay. As I told you, those additional terms are coming from expanding the equations in the cylindrical coordinates and using the fact that partial ER, okay, the unit vector in the R direction over partial theta is equal to theta, and partial the unit vector in the theta direction by partial theta is equal to minus R. Yeah, so using those two, and doing the math, you will get those additional terms. You see here, this one is an additional term, this one is an additional term. Here we have an additional one here. Okay. So yeah. Okay. So now let's do the derivatives for our components. What is the derivative of UR with respect to R? UR, again, it is C over K. Okay, let me here delete and delete and delete. This is the hydrostatic. We don't need it, as I told you before. So partial U R by partial R is equal to minus C over R squared. Yes, because it is C over R. Derive it with respect to R, so it is minus C over R squared. And then outside multiplied by UR. Okay, remember these are the convective acceleration terms. Okay, the convective acceleration, this is the local. So all the local accelerations are zero because we have steady state. And the convective accelerations, okay, which are also the nonlinear terms in the equation, because we have a derivative multiplied by the function itself. A derivative multiplied by a function. This is nonlinear. Derivative multiplied by a function. But second derivative is linear. Okay, so this is linear. This is second derivative. This is second derivative. Also, it's linear. Second derivative, second derivative, second derivative, second derivative is linear. Okay, but a derivative multiplied by a function is nonlinear. So these are the nonlinear terms in the Navier-Stokes equation, the nonlinear terms. So now multiply by the function itself, which is C over R. So we'll end up with this term being in the end minus C squared, yes, over R cubed, yes. And this one here is U squared. What is U squared? U theta squared. U theta was K over R. So when we square it, we will have K squared over R squared. And then divide by R again. So R squared. And then you will have R squared also here in the denominator. Okay. So it will be R cubed, okay, multiplied by it. So K squared over R cubed. We can add those two because they have here common. Okay. So we will have the convective terms. In the end will be rho K squared, yeah, minus C squared. Okay, or here we have also here minus. So minus K squared minus C squared over R cubed. Yes, so this is the convective terms. Now let's look here in the viscous forces. These are the viscous forces, and they are denoted by the Laplacian operator. Okay, Laplacian operator of V. So if we expand it in the cylindrical coordinates, this is what we get. Let's do this one first. So partial U by partial R, we said before, it is minus C over R squared. And then when you multiply here with this R, what happens? This R will cancel the R squared in the bottom. So you will be only left up with R. So for now, we have C over R and the minus, yeah? The R outside canceled the square after I derived, of course. And now again, derive with respect to R, and after you derive, multiply by 1 over R. So what's the derivative with respect to R now? The derivative with respect to R for UR, it is going to be minus, and then multiply again by minus, so it's positive, C over R squared, and then multiply by 1 over R outside, so it is C over R cubed. Okay, so all of this is C over R cubed. Now this is UR, which is again C over R, and then C over R squared, so it is R cubed now. So we will end up with C over R cubed. What happens? here we have a minus, so those both terms cancel each other. So the viscous forces in the R component are 0, okay, or the net viscous forces. In the end, the R momentum equation will yield minus partial P by partial R equal to, let me take the minus outside here for this one, rho K square plus C square over R cubed. And let me again delete this. Okay, I hope you can see it. So take the minus with the minus and you will end up with the pressure variation, okay, with respect to R. This is the equation that describes that. Now integrate with respect to R. So the pressure, okay, is equal to rho K squared, yes, K squared plus C squared. And what is the integral of R to the power minus 3? It is R to the power minus 2 over minus 2, yes? So here we have R squared minus 2, I will take it down. And here we have minus half outside. So minus half rho K squared plus C squared over R squared. This is P. Plus, of course, a function this time of theta, because we integrated with respect to R. Now let us continue and do the same thing exactly for the theta momentum equation to find this constant f of theta. Okay, so still we have this here. Okay, now let's evaluate all the terms. U theta by partial U theta by partial R. Okay, I'm going to do this one quickly because it is the exact same thing. It is going to be K, yes, K now, over R squared minus, and then multiplied by UR, which is C over R. So we'll have here K C R cubed minus outside. Okay, and now this term, U multiplied by theta, UR and multiplied by U theta. So we have K over R multiplied by C over R, K over R multiplied by C over R, divided by R. It will be equal to K C over R squared over R. So it is K C over R cubed. Yes, so K C over R cubed. Look, this term is exactly the same as this term, but with a negative sign. So the convective acceleration in the theta component is 0. Okay. Now let's look at the viscous forces. The viscous forces for now, we have U theta over R squared. What is U theta? U theta is K over R divided by R squared, so it is going to be R cubed. We have a minus outside. Do the same exact thing as we did before here. So you partial U theta by partial R. What is it going to be? It is going to be K minus over R squared multiplied by R. Now omit the square here down, and now derived again with respect to R. So the square will appear again, but now minus minus, so it will be positive. Then again by 1 over R outside, so it is going to be R cubed. And now notice how this is equivalent to this, but with a minus sign. So also the viscous forces is 0 in the theta component. Okay, so now we can say that the variation of pressure with respect to theta is equal to 0. Of course, I can omit this one because I can multiply both sides by R. So I'll end up that the variation of theta with respect to, or the variation of the pressure with respect to theta is equal to 0. And if I did or derive the pressure relationship that I got before with respect to theta, okay, to make the equality. So this is the pressure relationship that we got from before. Derive it with respect to theta to get this constant. So if you derive it with respect to theta, this term will be gone, and you'll end up with f prime of theta. So it is equal to, okay, and partial p by partial theta, which is equal to 0, is equal to a function prime of theta. So what is f theta? It is a constant, yeah, because its derivative is 0. So what is it? It is a constant in the end. Okay, so it is a constant. Okay, because if you integrated 0, it will give you 0 and then plus a constant. So constant. So now I knew what is f theta. Now all what's left for us is to write the relationship p of r and theta equal to minus half rho k square plus c square over r squared plus a constant. Okay, and we can observe something from the beginning of the problem, that our velocity field, okay, our velocity field, which was c over r, okay, er plus k over r e theta and plus 0. Okay, so I don't need it. This is an irrotational flow. Okay, how can we know that this is an irrotational flow? You will come to it in chapter 10, that the vorticity, okay, vorticity or the curl of the velocity field is equal to 0. Okay, the curl is equal to 0. Okay, you also done this in chapter 4, fluid mechanics. But if you do the math, you will find that the curl is equal to 0. Okay, and the cylindrical coordinates. So what does the curl being equal to 0 mean for us? Remember, what are the assumptions to use Bernoulli's equation? The flow should be steady. The flow should be incompressible. Okay, along a streamline, of course, a Newtonian fluid, and also the flow should be irrotational. Okay, so if the flow is rotational, we cannot apply Navier-Stokes. We cannot use Bernoulli's equation. And the flow being irrotational, this means that the viscous forces are negligible. Okay, the flow being irrotational, this means that the viscous forces are negligible. Okay, maybe it was not called irrotational, it was called we don't have viscous forces or negligible viscous forces. So this is, and when the flow is irrotational, then there is no viscous forces essentially, because just think of it. Okay, now these are maybe the particles that constitute the fluid, and now they do not rotate, or we don't have a rate of rotation for them. So they are keeping moving in this straight line, smooth lines. So they do not make friction with each other. Okay, so this what makes the viscous forces equal to 0. And also you can see it from this also agrees with what we found or what we calculated from here. Because look, the viscous forces were 0, the viscous forces were 0, and only the convective terms were present here, and here we didn't have convective terms. Okay, so this does agree with what we did before, or what we did in this problem. So let's do Bernoulli's equation, okay, between 2 points on this polar flow. Okay, let's do Bernoulli's equation between 2 points. Maybe I will select a point here and point here, whatever. So P, okay, delta P will be equal to half, yeah, rho, okay, K, no. Let me do it step by step. So P1 plus half rho V squared 1, yeah, plus Z1. Of course, my flow is in the plane, so the Z is constant. P2 plus half rho V2 square plus Z2. So also this one is not present. So my delta P will be equal to half, okay, or P1 minus P2. It's going to be half rho V2 minus V1. So it is in the minus direction if you want here to make it P1 minus 2. Okay, or if you want to make it 2 minus 1, then it's going to have a positive sign. Okay, so rho V1 squared minus V2 squared. Okay, so this is delta V squared, yes, or not? It is V1 squared minus V2 squared. This is equivalent to, if you want to make it from our flow here. Okay, so let's put it in this way. Okay, our velocity magnitude or velocity components together is going to be K over R, the resultant, sorry, plus C over R squared. Yes, this is the resultant velocity, what it will be. So yeah, this is it. And then plug it here. Okay, plug it in here. Let me just take for convenience that V2 is 0. Okay, for now. Let's say that it is the velocity here in the center. Okay, so take it as 0. Or let's say that it is the velocity far away, sorry, not in the center, very far away. So it is going to be here infinity and infinity, so you'll end up with 0 and 0. So what will happen is that half the pressure differential, it will be equal to minus half rho, and now square this root, you will end up with R square here in the bottom, K square plus C square, which is essentially the exact same thing. Okay. Now this is P, okay, P minus P infinity. Yes, because I told you, now let me take P2 to be in the infinite or at infinite. And now compare what we have got, okay, or our result, okay, from here with this. So it is exactly the same thing. And now we can deduce that the C is nothing but P infinite, okay? Because substitute here infinite, you are going to end up with 0. And then this is essentially P infinite, nothing else. So yeah, and remember that this is the pressure field in the plane, because we also have the hydrostatic pressure, which is inside and out. But that one is of no use for us in this problem, because we are asked to find only this one, and that the hydrostatic pressure will be equal to rho gz, okay, the difference in the z direction, if we have a difference. Yes, and just to tell you, or to make you know, this problem is, or it's a model, okay, of the tornado, okay, of a tornado. So if we have a tornado, okay, that is whirling or swirling like this. So this is the center of the tornado, or the eye of the tornado, okay, and this is the velocities, okay, the UR and the U theta, okay. And when the R is far, okay, when R approaches infinity, we have P infinity, okay, and this pressure variation represent the pressure in each concentric, okay, circle along the length of the tornado, okay, but not like this. The pressure differential in this direction is going to be the hydrostatic pressure. So yeah, I think by this we are done. Next time we will solve Navier Stokes, or we will solve problems with boundary conditions, but we are not only asked to find the pressure field, we are asked to find other velocity components, okay? And you will solve tomorrow, inshallah, with Professor Khalid, the problem with this one, I think, flow in between flow and pipe, I guess, and you'll have boundary conditions. Here you have velocity is equal to 0 because of the no slip condition, and here the velocity is equal to 0, and here the velocity is maximum, okay? And yeah, so see how it goes with you on Tuesday, and I think also on, I don't know if Thursday we're going to continue or take a new topic, but next time we'll continue with more problems that involve different cases, okay? See you next time, inshallah. Assalamu alaikum.